Hi and welcome to my channel. If you've not joined before, and I suspect some of the Year 9s who this is intended for won't have done. So first lesson for those people who have not seen this before, and for those who are returning and just coming back for a bit of revision. Hi, I'm glad to see you here. And we're going to be looking today at the Group 1, the Alkali Metals, from Topic 1. So this is currently Lesson 8 in Topic 1. So what we're going to be learning about are the characteristic properties of the Group 1 elements, some of the causes of those properties, in particular looking at the reactivities, the reactions with oxygen, water and chlorine, the trends in the properties and the trends in the reactivity as we go down the group, and the reason for those patterns or that trend. The alkali metals. They're found on the far left column of the periodic table, the very, very left one, going from top to bottom. They consist of lithium, sodium, potassium, rubidium, cesium and francium. And their symbols are Li for lithium, Na for sodium, K for potassium, Rb for rubidium, Cs for cesium and Fr for francium. Now I believe that Na stands for natrium, which is the German for sodium, and K is kalium, which I think also is the German, and that's just because of the international symbols. They're called the alkali metals because when they react with water they form alkali solutions, so that's nice and simple. So they're alkali metals because they make alkali things when they react. Now looking at the properties, we're going to look at some of the properties, or you could also say these are the characteristics of them, what they have about them. So they all conduct heat and electricity. Just like any metal, they conduct heat and electricity. They all look shiny and metallic when freshly cut, just like all the other metals. They mostly look silver as well, although I believe that the cesium can take on a slight goldish hue. They all react to make alkali solutions, which we've already discussed, and they're all really reactive, even for metals, and so they're stored generally in oil, which stops them reacting with the oxygen and the water in the air and the atmosphere around it. It forms a protective coating. Well, that's certainly the case for sodium, lithium and potassium. When you get onto things like cesium and rubidium, though, they tend to be stored in an inert gas environment, something like argon, because they're so reactive they will even react with things that are dissolved in the oil and potentially the oil itself. They've also got low densities. The first three, sodium, lithium and potassium, will actually float on water. So you can get a big lump of it, a big chunk of these things, and it will float on water. And they're all fairly soft for metals. They start off, actually, lithium is the hardest, and that takes a little bit of effort, but you can still cut through it with a scalpel. Sodium is significantly easier, and by the time you get down to potassium, you can start to rip this apart with your hands. You can probably cut through it with a ruler. It's that soft, and then those properties continue going down the group. They get very, very soft. They've also got low melting points for metals. In fact, I have seen that cesium on a warm day, cesium on have to be a fairly hot day, will actually melt. Now, reactivity. So we're talking about what it's going to do when we make them react. And generally what we find is that lithium, when we look in water, it floats around on the surface, it fizzes vigorously, releasing a gas, so it reacts quite well. Sodium reacts even more vigorously, and the heat generated from that reaction is in fact even enough to melt the sodium, and it forms into a sphere, and because it floats around on the surface and really whizzes around. Potassium bursts into lilac coloured flames on contact with water, so yet even more reactive. Rubidium and cesium both explode on contact with water to less, well, rubidium not so much as cesium. Cesium really quite a violent reaction with water. So we can see that as we go down the groups, they tend to get more reactive, and that's trend number one. As we go down the groups, they get more reactive. So why have I not covered francium? The reason why I've not covered francium is it's incredibly radioactive, and that means it's very hard to get hold of. I think the half-life is only something like, I could be wrong here, about 10 or 12 minutes or something like that. So that means if you've got, say, a gram of it, 10 minutes later you'll have half a gram because of radioactive decay. So it's very radioactive. You don't really want to be using it, so you can forget the idea we'll ever get that in school and be dropping it in water. There are some videos on YouTube which are supposed to show or claim themselves to be francium in water, and it's actually what it's showing is an atomic bomb that's underwater. It's nothing to do with francium. So the trend is alkali metals get more reactive down the group. You need to know that. That is an important part and it can be examined. You are expected to be able to talk about the alkali metals. It might say compare lithium with potassium and their reactivities, and it wants you to say that potassium is more reactive because it's further down the group. Why are they so reactive then? The reactivity comes down to the electronic structure. Chemistry is all about electrons. All the alkali metals have only got one electron in their outer shell, and again that's something that you should know for the exam, so you need to learn that. The group number also tells you how many electrons are in an element's outer shell. So these are the alkali metals, they're group 1, they've got one electron in their outer shell. The group 2 elements have got 2 electrons in their outer shell. The group 3 elements have got 3 electrons in the outer shell. How many do you think group 4 have got in? Yep, 4. That's simple, isn't it? That single electron, though, in the group 1 elements, the alkali metals, explains the reactivity of them. So as we go down the group, we add an extra shell of electrons. So that shell of electrons gets added on, which pushes the outer electron further and further away from the nucleus. And the alkali metals don't really want to have this outer electron in its the single electron in its outer shell. They're quite happy to get rid of it. And the further away it goes from the nucleus, it means it doesn't feel so much of a force of attraction to the nucleus. And if we remember, in the nucleus we have protons which have got a positive charge. Electrons have got a negative charge and opposites attract. So as the electron gets further away from the nucleus, it's less and less attracted to it, so it's easier to pull it away. And that means the electron is easier to lose, which means the atoms get more reactive as we go down the periodic table in group 1. Trends in the melting and boiling points and the relative atomic masses. So the melting points and boiling points, we're going to cover those together because they do exactly the same thing. They go down as we go down the group. So the melting point gets lower, the boiling point gets lower. So lithium has the highest melting point and boiling point. Francium is estimated to have the lowest and would in fact be a liquid at room temperature, because one of the estimated melting points and boiling points I've read for it is 8 degrees, the other one was about 20 degrees. So francium we would estimate would be a liquid or close to a liquid at room temperature. So very similar to mercury. Moving on to the relative atomic masses now. The metals gain protons and neutrons as we go down the group, and protons and neutrons, as we can remember, have a mass, whereas a significant mass compared to electrons. So obviously if they're gaining protons and neutrons, they're also gaining electrons at the same time. So their masses increase as we go down the group. So, summary. Melting points decrease down the group, relative atomic masses increase down the group. Now we're going to have a look at some of the reactions in a bit more detail. So, they react with non-metals to form ionic compounds, and you'll learn more about ionic compounds in topic 2. What happens here is the alkali metal gives away its single outer electron to the non-metal. So it gives it away, doesn't want it. And this creates two oppositely charged ions, things called ions, which attract each other. So because the metal has got a neutral charge to begin with, and then it gives away a single electron, it now has a positive charge because the electrons have got a negative charge on them, so it's lost a negative. The non-metal has gained that negative charge, so it ends up with a negative charge, and those two oppositely charged ions are going to attract each other because opposites attract, and that binds them together in a compound. So when we're looking at how the group 1 metals make their bonds, how they react, the first step is we are going to draw the electron structure, and this is something that you should have already done, so we'll only cover it briefly. The first step I like to do is I like to do a circle, and in the middle of that first circle I put my elements symbol, so Na for sodium there. The next step is I'm going to make this the first shell of electrons, and I need to start filling my electron shell up. And I look at sodium and I look down the periodic table, and I know it's got 11 electrons because its atomic number is 11, and if its atomic number is 11 it's got 11 protons and it's got 11 electrons. I also know that the first shell can only fit 2 electrons in, so I'm going to do those as crosses. So there are my first 2 out of the 11 electrons. I need to do another 9 to take me up to 11. So I'm going to draw a next shell of electrons around the outside of that. And we should know that the second shell of electrons can hold 8 electrons, so I can now put those in. One at 12 o'clock, one at 6 o'clock, then one at 3 and one at 9. So that's only 1, 2, 3, 4, 5, 6 so far. So I'll go for 7, 8, 9, 10. Still missing 1. So I draw my outer shell of electrons and I put my 1 electron there. Now this top electron up here, this one, the outer one, can be lost if there's something to go to. And an example of something it might go to might be, for example, the element fluorine. So element fluorine is just F, and fluorine has got 7 electrons. I'm going to draw these as dots so we can distinguish them. 1, 2, 3, 4, 5, 6, 7 electrons. So the sodium can donate this electron here to the fluorine. And what this leads to, when this happens, so it's given that electron away, is we end up with the sodium. Now we tend to draw these in square brackets. But the sodium still has its first shell, and it still has its second shell of electrons. But it's lost that outer electron shell and it's lost that outer electron. The electron's got a negative charge, so if a negative charge has left this amount and left this atom, it's now going to have a positive charge. So what we're also left with is we're left with our fluorine, and our fluorine has gained that electron from the sodium. There it is. And because it's gained a negative charge, it now has a negative charge overall, and those two things attached. This is a sodium ion, and this is a fluorine, or fluoride ion I should say. So sodium ion and fluoride ion. So you might have heard fluoride in your toothpaste. It's the same kind of stuff as this. It's got F- in it somehow. You will learn more about this in topic 2, bonding, so don't worry about it too much, but this is just the basics of what I mean. That they're reactive because they can lose this outer electron. They've got 1 electron in the outer shell. They can lose it very easily. That makes them reactive. Now looking at the specifics of alkali metals and oxygen. It's a quick reaction. If you get an alkali metal, you take it out of the oil, so even lithium, which is the least reactive, and you clean the oil layer off, especially if you slice open a fresh bit to expose a fresh bit of lithium to the air, it reacts within a matter of seconds to form a dull grey coating. It probably takes about 30-40 seconds to happen. This happens even quicker if you set it to light or heat it, obviously. So they all burn with distinctive colours as well, and that's an experiment I like to do. What happens is 2 alkali metals, so this is generally what happens, 2 alkali metals each give their outer electron to the oxygen, to a single oxygen, and it forms an alkali metal oxide. And to find the name of the oxide, you just take the name of the alkali metal and add oxide after it. So if I was to take lithium and react that with oxygen, I would get lithium oxide. If I was to do it with cesium, I'd get cesium oxide. Really, really easy. Okay, so the naming of the oxides, really easy. Just take the name of the alkali metal, put oxide after it. And this is what it looks like in terms of symbol and word equations. So if we get lithium plus oxygen makes lithium oxide. That is our word equation. Now we need to turn it into a symbol equation, so we need to find out the symbols for lithium. So the symbol for lithium is Li, symbol for oxygen is O, but we're talking about oxygen gas in the atmosphere, and that is O2. There's no reason necessarily now you would know what the formula for lithium oxide is, so I'll give that to you. It's Li2O. The next step is we need to balance this equation. This equation isn't balanced. If we have a look here, we have 1 lithium on the left. We have 2 lithiums on the right because we've got Li2. The little 2 after the lithium says we've got 2 lithiums. We can't put a little 2 after the lithium here because that would change the compound. So we can only use a big number. So my first step is I put a 2 in front of the lithium. So now I've got 2 lithiums and I've got 2 lithiums. But over on this side I've got 2 oxygens, O2, 2 oxygens, and I've only got 1 oxygen on this side. So I need to do something here to balance them out again. So I need double the amount of oxygens on this side to make sure I've got the same amount on this side. So I put a big number 2 in front of there. That would give me 2 oxygens. But it would also give me 2 times 2, 4 lithiums. So the total balanced equation is this here. 4 lithium plus oxygen makes 2 lithium oxides, or 4 Li plus O2 makes 2 Li2O. Now, I will do a video on balancing equations specifically. If you think that's a good idea, leave a comment down below. If you struggle with balancing equations, let me know. Does take practice. I remember balancing equations when I was at school and finding it really, really difficult, and then all of a sudden it just clicked and I was like, okay, this is actually really easy. A lot of the time I think people think it's going to be more complicated than it is, and therefore decide they're not understanding something when it is actually very, very simple. So we will go through it and we will make sure that you can get some good practice and get good with balancing equations, because it makes chemistry really easy. All the other alkali metals react in exactly the same way. So instead of having lithium or oxygen there, lithium plus oxygen there, you could have cesium plus oxygen makes cesium oxide, and then we'd just change these symbols. So instead of 4 Li, it'd be 4 Cs. Instead of 2 Li2O, it would be 2 Cs2O. Really, really simple. Okay, so you just substitute the symbol of your choice where the Li is in this example above. Now, the reactions with water, which you have probably seen a few times throughout your science lessons. So when we react an alkali metal with water, we always form an alkali metal hydroxide and hydrogen, which is a gas. So the reaction looks like alkali metal plus water makes alkali metal hydroxide plus hydrogen. An example is lithium plus water makes lithium hydroxide plus hydrogen. And again, you can just substitute any other alkali metal in for lithium. The balanced equation for this would be 2 lithiums plus 2 H2Os, waters, makes 2 lithium hydroxides, LiOH is lithium hydroxide, plus H2. And we can make that even better with 2 LiS in brackets to show it's a solid, plus 2 H2O in brackets L for liquid, makes 2 LiOH aqueous plus H2 gas. Okay, so we'll come on to that in a second. Now, reactions with chlorine. These are vigorous reactions, especially when heated. They do really, really bright lights, and obviously I can't do one right now. I'd love to be able to do one next time I'm back in school, but unfortunately I'd need to prep the chlorine gas the day before, so I don't think I'm going to get a chance until lockdown's ended. But it makes a metal chloride salt, or an alkali metal chloride salt it should say. So if we get our alkali metal, we react it with chlorine, we make an alkali metal chloride salt. Example, lithium plus chlorine makes lithium chloride. Potassium plus chlorine would make potassium chloride. Again, you can just substitute it. The symbol equation, 2 lithiums plus 1 chlorine, Cl2, because again it goes round in a pair. Chlorine always goes round in a pair when it's a gas. So by itself, you never see Cl by itself, it's always Cl2. And that makes 2 lithium chlorides. And again, the reaction gets more vigorous down the group, just like with the oxygen, just like with the water. As we go down the group from lithium to sodium to potassium to rubidium to cesium, the reactions get more vigorous. For the symbol and word equations, for any of the alkali metals, you just substitute the right symbol and the right name into those equations. It's dead simple. Now a little bonus, state symbols. Now we had a look at these, not last slide, but the slide before, and they should be in all symbol equations, these things called state symbols. And what they do is they tell us the state of a species in equation. Okay, and these are the state symbols. So S, L, G, A, Q. So have a little think. Can you figure out what they mean? So S is for solid. So when you see in a chemical equation a little S in a bracket like that, it means whatever it is a solid. What do you think the L means? Yep, liquid. The G, fairly obvious, gas. The only tricky one is AQ, and I did mention it last time, it's aqueous. And what aqueous means is it means it's dissolved in water. So if you see AQ after a chemical in an equation, it means that species, that chemical, has been dissolved in water. Now, quick summary. We've covered today that the group 1, our alkali metals, are the far left column on the periodic table. They all have one electron in their outer shell. This electron is what makes them particularly reactive, because it's easy to lose. They get more reactive down the group because as we go down the group, the outer electron gets further away from the nucleus and is easier to be lost. They react with chlorine to form chloride salts. They react with oxygen to form oxides. They react with water to form hydroxides and hydrogen. Okay guys, I hope you've enjoyed this video and found it useful. Please remember to subscribe if you've not done so already. If you're a new subscriber, hello, good to see you. Please also remember to like this video and share it with anyone that you think might find it useful or interesting. I hope to see you soon. I hope you're all doing well during the lockdown and during the COVID-19. I hope to see you back in school soon. Okay, take care. Bye bye guys.